kick us off here. So thank you everyone for coming out to the first exoVAST of 2024. So as a reminder, these are talks about astronomy software specifically related to exoplanet science. So we have a great speaker today, Vincent Kofman, who is an assistant research professor at American University and a scientist here at NASA Goddard, who will be talking about the Planetary Spectrum Generator. And we have these exoplanet related VAST talks the first Wednesday of every month at 11 a.m. Eastern time. So be sure to check out the next one when we have the details announced. And then there is also the regular VAST, the virtual astronomy software talks that are the third Wednesday of each month. So if you're interested in non-exoplanet software, definitely check those out. But Vincent, very excited to have you here. Thanks again for coming out and talking to us, and I will turn it over to you.
All right, thanks, Joe. Thanks for inviting me here. Thanks for giving me the opportunity to talk here. I actually have some exciting news because I submitted the manuscript that details a lot of this work on Friday. So happy to now talk here. Toby, did you have your hand up? Like, if there's questions during talk, maybe we can put them in a chat. I'll try and
Sorry, it was an accident.
Oh, okay, no worries. Yeah, so questions in the chat, and then I'll do a demonstration at the end, so that we'll have some more time to go in a little more depth there. Okay, so yeah, I want to notify here, or like acknowledge the team here. A lot of this work has been obviously the whole team has been involved here. It's being led mostly by Geronimo, Toma, myself, and then I want to specifically acknowledge here the work of my high school student Tanvi Deshmukh, who's been doing a lot of code testing, and she's been actually working on some simulations, and hopefully we'll be able to send a manuscript out about that in the coming year. Anyway, so yeah, the Planetary Spectrum Generator to study exoplanets, that's a very broad title. I really want to focus a little bit on some of the 3D aspects that we've been developing heavily over the last couple of years, and really been testing over the last year, and that's where most of this talk will be focused on. So, kind of on slides here, the Planetary Spectrum Generator. The online interface is maybe familiar to some of you, or what it looks like is you have the interface here on the right. This is a screenshot of the web page, and we'll go there later. But there's a couple of important things that I wanted to point out here. We have the object, we have the composition, and the instrument. So those are sort of the three steps that you should keep in mind, and that sort of links to the possibilities as well. So the Planetary Spectrum Generator was originally set up as a sort of a collection of tools that was mostly studying solar system objects, so comets and Mars in particular. Geronimo has always explained to this as like it's his frustration with people not willing to share codes, like interoperability between some IDL code that this guy wrote and that Python code that guy wrote, and at some point it was just okay, I want to share what we've done, and I want to find a way to do that. And then he started developing the Planetary Spectrum Generator. And yeah, as I've been saying, it's a free radio transfer tool. You can do UV to the radio. There's different elements of observatories in there as well. So you can do space-based telescope, ground-based telescopes. Large difference there is of course in the resolution that you can reach with a ground-based telescope, because you can build them much bigger, and the instrumentation is much more accessible by engineers, so you can be a little bit more risky in that sense. But of course, for ground-based observations, you have to look through the atmosphere, which is a particular problem in the infrared. Then orbiters also an object we can study. Yeah, so it contains solar system objects and all confirmed exoplanets. We have a noise simulator, which we don't have time to go into in detail here, but please feel free to ask me about that at any time after this. And the manuscript that we've submitted goes into a little bit of detail there too. We can also do retrievals with PSG. We were using grid-based methods. And if you want to get really advanced, you can even take PSG, and you can essentially download an object which is called a Docker container. So this Docker container allows you to run PSG on your own machine, and that removes some limitations in terms of computational time, as well as limitations to how many calls you can make. I'm talking about these calls, but what that means is normally you work on the interface, right? You hit generate spectra and you get your outputs. But the alternative is that you send essentially your command file or your configuration file to the computer that hosts PSG, and it'll send you the results back. And then the Docker version allows you to do it on your own machine, which I had to do for a lot of the simulations here. And I want to particularly focus here on the globes module, which is a method to ingest global circulation models. And these global circulation models you can then use to generate 3D spectra. We also have help desk, or not help desk, help videos, tutorial videos. There is a very detailed manual. It's the book that there's some images here. It's available online. It's on the under the help button. Geronimo updates this regularly, so I always go to the website and just upload or download the latest version. We do have a couple of paper copies as well, but I would say they're already outdated because they've been printed beginning of 2022. So anyway, the information's online. That's where I recommend you go. So yeah, the outline of the talk here, I wanted to go over 3 use cases. So we have a transiting planet, will be a little shorter. Then observations of direct imaging, that's an Earth-like planet, and then there's a phase curve of TRAPPIST-1b that we've made for the paper that Thomas is writing about globes, which we're close to submitting. And I wanted to go into a little bit more of examples there for that case. And I do here have noise simulation detectability on that, but I don't think we'll have time to go into that, but I can show a couple of things about that too. But first, before we go into the use cases, I wanted to go over the general principles of PSG and globes, because I think that is a helpful point to start. Because globes is you use it with a slightly different strategy of PSGs, particularly if you want to do like a sort of a series of simulations. Okay, so just to sort of capture up on the basics and where these elements are being captured in PSG. In order to model atmospheric absorption, there's these essentially the three things that I've been talking about, right? You have your object, you have your radio transfer code, and you have your detector essentially, or your instrument and detector combination. So in PSG, those were the 3 buttons, right? So we have ephemeris and the flux calculation. So those are all the geometry things that you need to consider. What planets are we looking at? All that kind of stuff. Then the radius transfer code, we can go into a lot of detail there, but I'm going to spare you most of that. But we'll go over a couple of elements, but that's obviously that's where the bulk of the work has been in developing PSG. But I think the way that it's set up now, it's the website and the globes interface essentially are a wrapper to the radius transfer code, and so are the ephemeris and the flux calculations, right? So all of these essentially feed into the radius transfer code, and that's where you get your results from. Then the instrument detector and noise model, those are essentially just also like layers you put over the radius transfer code, because the radius transfer code essentially gives you photons back. And then the question is like, how can you detect these photons, right? Like what wavelength range are you sensitive to? What's the throughput of your instrument and all that stuff? So the operating principles, we work with a configuration file, and I'll show an example of that later. But essentially, the configuration file it contains all of the elements you need to do to run the full simulation, and it's in that sense it's a reproducible, shareable, and easily modifiable element of the code. So right, so if you have a question, let's say about PSG, you go to our Slack channel, you post a question, it's like, oh hey, I want to look at TRAPPIST-1c in transit, but I'm getting an error here. If you send us the configuration file, we know exactly what calculation you're doing, how you're doing these, and what kind of elements you might be selecting, or you know where possible misinterpretations come from. And that is I will say that first, the misinterpretations about like the settings in the configuration file are not unique to users. I make a lot of mistakes, and there's a lot of sort of complicated complications that you get when you're thinking about observing planets, when you're like, okay, are we talking about especially for the globe situation, right? Are we talking about a sphere, and are we looking at the subsolar point and the sub-observer point? Are there like, can we define the entire observations based on that? Or in some cases, it might make more sense to just look at the face of where is the planet in the face of the orbit, right? So anyway, there's a lot of it's a very complicated tool, obviously, and the configuration files are the way to access this. And the shareable aspect is really helpful. And I would say, like, if there's ever any confusions, like, you're not alone. It's a complicated tool, and how often I walked into a Geronimo's office asking, it's like, why is it, what is it doing here? What am I doing wrong? I'm telling it to do it in this phase. Why is it not doing it? It's like, well, in this case, there's a priority situation for this and this. Anyway, so I'm rambling here. So let's continue. Now we're going into the use cases. So if we're thinking about planetary, exoplanetary exploration, right? There's for this case, we're looking at three different cases, as I mentioned. For transit cases, and then again, we will be talking specifically about the 3D aspect or the globes aspect here. The planet goes in front of the star, obviously, and in order to sort of constrain what you're getting back, you need to mostly follow the extinction of light across the atmosphere. So you're mostly interested in how does the light make it from point A to point B, right? So let me pull up the laser pointer here. So yeah, point A to point B. And obviously there is, the laser point's not working here. So I'll clear my drawings and get back to just using my cursor. Yeah, what we need to consider here is layering, spherical effects, and refraction of light. Ideally, of course, like if you think about the system in a very simple way, you're just looking at light coming through the atmosphere. But unfortunately, there's a whole bunch of effects that we need to consider here, and we don't have to go into details here. But essentially, there's a lot more to it than just obviously a single object with with absorption in there. But there's a bunch of different things you need to consider with like the refraction of light and where the light hits the surface and where it hits like potentially cloud layers. So the paper that we're now working on with Thomas is going into a little more in detail here. I've shown here sort of a sketch of how we would do this in globes. So essentially, there's just two ways you can do this, right? You could do this as you could assume that the atmosphere is homogeneous throughout the planet. And then you take this 1D profile and you see how much the light gets essentially how much extinction you get as the light goes from the star to the observer, right? As many people know on this call, there's extensive studies on how the atmosphere of a planet looks like and what the 3D effects are of what's going on in the atmosphere, right? So what's like we're thinking about heat transport, we're thinking about clouds. And for transit case, you can imagine that if the planet transits in front of a star, you might get more cloudy situations around the equator versus at the poles. So in that sense, the 3D effect, and that's what we see here in this figure, the 3D effects are pretty relevant here. So we're talking here, and in this image, we're talking about binning. So binning is essentially how many, if we put a GCM into PSG, and I'll show you later how that works. The binning essentially tells you in what is how many boxes do we take to get to the average of where the light comes through. So if we do a binning of 10, we essentially take a number like 10 boxes, essentially 10 of these GCM boxes, and we calculate the light going through that. Now, what we see in this figure is if we're looking at the atmospheric transit depth as a function of wavelength, we see that the baseline or the atmospheric depth to which you can probe makes a big difference what your binning is. So if you have a very high binning, your clouds essentially are spread out over the entire surface, so they're not that relevant. But once you start considering the full resolution, what you see is actually that the positioning of the clouds is clearly making a difference here, because you're getting a lot less light back than what you expect. Okay, so that was for the transit case. Now for the direct imaging situations, direct imaging is a little more complicated because instead of just looking at extinction, you have to constrain the intensity essentially. What do I mean with that? So we're looking at, in this case, for direct imaging, we're looking at reflected light. Reflected light can be scattered as well as just reflected. So scattering, like think about clouds, and think about Rayleigh scattering, for instance, blue sky, right? Like even though there's no light at the location, there's no light coming directly from the location in terms of sunlight, right? We do see blue light across the entire atmosphere. So we need to consider how much of that light makes it back towards the observer. Then for the surface, typically you can assume a lumbration surface for solids essentially. But as soon as you start adding a liquid water body, you need to figure out how you model the reflective specular reflection of the ocean, so glint essentially. And then especially for the case of Earth, which we'll go through in a lot more detail here, we get really strong local variations that dominate the spectra. So we're gonna show here that I think that the 1D approximation is insufficient. So I show this complicated figure here, right? We have here the sun. It's at the top. The color is inverted here because it comes from a handbook. And we're talking here about a number of streams. So the streams essentially just tells you about how much computational power you put into tracking these photons. So here in this case we have 4 streams. So that comes from N2, which is it's a symmetrical system in this case. So you're considering the light coming from several different angles essentially into what you're collecting. And I always struggle like conceptually, like it took me a while to get this effect like well understood, but by playing around with it a little bit, I did get an appreciation for it. So that the handbook goes into a little more detail, and the papers that we're now working on as well. So it's a little too complicated to go into here at the moment because there's all these technical terms that really don't make a whole lot of like scientific sense to talk about. So okay, so clouds and 3D modeling. Why are we interested in clouds, right? Well, the argument that I'm making here is, well, most of our atmospheres or actually all of the atmospheres in our solar system do contain clouds. So the 3D effects are very relevant there, right? And that you see also in molecules vary in position height on the Earth. For instance, we know that ozone is concentrated pretty high up in the atmosphere. Water is concentrated lower in the atmosphere. So those are relevant things that we need to take into account, right? And a simple 1D structure might not comprise describe that very well. So then what I mentioned here, right? The 3D clouds are of critical importance in the atmosphere because of energy balance, composition, transport of water, of course, and detectability of molecular species. When I started like critically thinking about this image, it's actually like it's really cool. And here you see sort of the 3D effect, right? So if you're looking at the moon here, right? The moon is being illuminated by the sun, and you can see that the sun is like visibly below the horizon in this case, right? Because if the sun would be at the horizon, it would be illuminating the moon from the side. But in this case, it's what, like maybe 5 or 10 degrees below the horizon. But you can still see that there's a massive amount of light in the atmosphere, right? So I thought this image would describe sort of the relevance of the 3D aspects and the Rayleigh scattering here. So that's what I want to show. Then in terms of clouds, obviously it's even more complicated because you have clouds, different layers, different heights. So here we have an image of the Earth from the ISS, and you're looking here at clouds heights up to about 10 kilometers. And then there's all these small Apache clouds, which are much lower, right? And so yeah, this is what we'll be working on. This is what we describe in a lot of detail in the paper that we just submitted. So we're looking here at Earth as a laboratory. We figured, why not start with Earth? Earth is very well described. There's a whole bunch of very detailed models out there, and also there's a way to measure the Earth directly, right? So if we can prove that we can model the Earth using the monthly average ground coverage, and we're using detailed GCMs, it's called the MERA-2 database. So it's a retrospective climate database. So it essentially tweaks its performance based on actual weather, and like, oh, like there were clouds here, we didn't model them, let's see what's going on. And essentially it has snapshots of the Earth every 3 hours back to 1980. So we've been trying to reproduce this with using MERA. So what we've done is we've taken information from MERA and MODIS and essentially reproduced the Earth and added clouds as well. So this is the cloudless features. But I wanted to show you the varying ground cover, essentially ground and sea ice cover here as a function of month to month. And you see the subsolar point in terms of the specular reflection from the ocean here as well. Okay, so the GCM, right? The global climate model. It's essentially, the way I see it, it's a big box, and each of these boxes has a number for the amount of water, the amount of ozone, pressure, and temperature. And we have here a resolution, so longitudinal, so east-west, 144 boxes, latitudinal 92, so north-south, and then vertical 72. And when we're looking at different abundances of water and ice clouds, so liquid water and ice clouds. Ice clouds are a little higher in the atmosphere, and molecular water and molecular O3 here. And the dots here indicate the height at which 90% of the molecules are below that height. So for water, you see that that's pretty low at 4 kilometers, and for O3, that's all the way up at 35. Anyway, let's proceed here to what this actually looks like. And I'm gonna, Joe, how am I doing on time, by the way?
You were doing great. We're at 22 right now, so
Okay. Okay,
we have
that's
the
good
whole
to know.
hour, so feel free.
Okay, perfect. Yeah, okay. So what we see here is these are our 3D simulations of the Earth, right? We have them on the left are simulations, and on the right are observations from a geostationary satellite. This is a Japanese water satellite, so that's hence the focus on this range. It's really like a tsunami predictor or the typhoon predictor, like bad weather warnings, heads up. But we have these images, and we've been trying to reproduce the clouds deck, the clouds cloud abundances, and also how they move, right? So each of the images on the left, there's a 3-hour time lapse there between the images. And honestly, I was super happy when we got this to work, right? Because you see we capture most of the cloud features relatively well. We see that the subsolar or the specular reflection, like the oceanic reflection, works, I would say, very well. Like the size of the spot is good. The colors are slightly off, but that's a complication that we could explore further in the future. But it's really much of a headache, because I think what we're seeing as we're looking at a Terminator, and the Terminator we get essentially we get the red coloring you get at sunsets, right? So anyway, I would say this works well, and I was very happy with these results. But now let's go into the spectra, because that's where the science happens, right? So in this case, we're looking at 2 figures here. We have wavelength on the x-axis on both, and the apparent albedo, so it's essentially the reflectivity of the Earth, right? And we're looking at 300 nanometers to about 1,000 nanometers, and we're looking at the reflectance spectra in the range where potential future observatories, such as habitable worlds, would be sensitive. And the cool thing about adding clouds to these simulations is that you really see that the reflectivity as a function of the local time, or the universal time, changes by quite a bit. So there's about a factor 2 variation in the brightness, I would say, between as a function of time, but also even as a function of purely of ground coverage, right? So one of the biomarkers that is strategically targeted to sort of represent like a planet being inhabited is the vegetation right edge. So a lot of plants, in order to sort of maximize their performance, right, or their efficiency, they're trying to reflect as much infrared radiation, which is not energetic enough to generate essentially their sugars, right? They try and reflect as much of that out to space, but that gives a very clear edge between 700 and 800 nanometers, which is where their reflectivity maximizes. And you can see as a function of the local time that the reflectivity changes by quite a bit. So that's due to changes in coverage. So and in the top right here, I show the simulations for this case. So we're looking here at the northern summer, and the local times, or the universal times, like correspond to each of these images. And you'd have to do some quick math, I guess, to figure out which one is which. But we have the full details in the paper. So yeah, this is for the direct imaging situation, right? The other way to study exoplanets would be to do a phase curve. So in a phase curve, you essentially observe the planet as it goes around the star, and you're trying to get light back from the reflectivity of the planet throughout the phase, right? Now in this case, we're looking at a TRAPPIST-1b simulation. So this is from Martin Toubé's work. So Thomas was heavily involved with this. But essentially, what we're looking at is a tightly locked planet, which explains the crazy temperature difference here, right? So we're looking at a surface temperature on the sort of the permanent night side at 150 Kelvin, and on the subsolar or the substellar point almost 600 Kelvin. And as you can imagine, if you follow that planet throughout its phase, you'll see that that there's a quite strong difference between the the 1D and the 3D simulations, and we'll go through that a little bit more detail here. Yeah, so we have a tidal locked planet with a CO2 atmosphere. It's pretty thin. What we're doing in the phase curves, if we're looking both at the reflected and at the emitted light from the planet throughout its orbit. And the TRAPPIST host star is pretty cold, so the emission is mostly in infrared. And then the relevant aspect is the planet's black body emission. Now, in order to simulate this in PSG, we have the configuration file, which is sort of the central operating principle of PSG, right? But then now we have to supply it with a GCM file as well. And the detailed steps will be made available in those papers, or you can ask me, and then I'll try and quickly explain it. But there's a lot of steps to make these files, right? Like you have to go from a netcdf file from, let's say, Rocky 3D, ExoChem, or whichever your model is that you're using. And then you have to convert that into a PSG specific binary format, and I'll show quickly how that works, and I'll share some Python script. You can do that, and then you hit generate, and that's where the cool things start happening, right? So a little bit about the configuration file here. You can essentially group the different lines in the configuration file by the different types. So this describes the object. So these letters are a little small, but essentially we have the object, which is an exoplanet, it's TRAPPIST-1b, and I'm reading out the lines here. We have the object diameter in kilometers. We have the object gravity, and star type, temperature, etc. And then geometry, you can imagine those are similar things. We're talking about surface. There's a generator section, etc. So there's a full list available on the website, and that's always my go-to place when I was like, well, what do I need to change? How do I do it? So that's where we go then. Then specifically, sorry for the boring code here in the screen, but the most important thing, and this we're currently working pretty hard on document this in a little bit more detail. But the really important thing for the GCM and for globes is the atmosphere GCM parameters list. And essentially, this is a I always compare sort of like a cryptology key on how to decipher the GCM file that you're going to upload to PSG. And I will go to a little more detail that. So yeah, so the way that it works, right? You have these data cubes, and the GCM file, the way that you bring it into PSG is not as a netcdf file, but it is as a binary file. What that means is it's just a stream of bytes. It's a continuous nonstop list of numbers. And the only way to decrypt the binary file is if you tell PSG exactly what is at the binary file at which location. And we wrote this out in a little more detail I'm just going to script the end of the. Yeah, well, that didn't work very well. So this is there's a detailed description at the end of the slideshow, and I'll make these slides available to you all. But anyway, you see here that each of these numbers specifically refers to. I'm trying to move the zoom bar, so I'm clicking. But each of these numbers specifically refers to a specific aspect of the GCM field, essentially that you're trying to upload. So let me go back to where we were in the talk. Here we are. We're almost done. So okay. So now what I'll be showing is we're looking at again this tidally locked planet, right? And as you can imagine, if you do a 3D model versus a 1D model, you get a very strong difference in what the emission of the planet is, because if we're thinking about, like, the reflected light's pretty similar, right? I mean, there's still a 10% difference here, but that's not what I want to draw your attention to. I really want to draw your attention to the difference in essentially the 3D model and how much flux you get back in the infrared versus the 1D model. And we can send this as follow, right? The planet, and remember, at the substellar point is about 500 degrees. At the other point, it's about 300 or 150 Kelvin. Now, if you would take the average of that, the average planet has a temperature of about 300 Kelvin. So you get a black body emission in this range. So the maximum is around like 10 micron, not nanometers. Sorry about that. These are microns, about 10 micron. But if you start separating out the black body emissions from the different points, the substellar point is so much brighter that it completely outshadows any of the other points, essentially. So yeah, so we have the 3D model here is about 1,700 different points. So each of these little pixels here corresponds to a PSG simulation. And yeah, then the 1D model is you average, right, the entire disk. And this image here, I think shows it all, where we're looking here at the planet rotating through its phase. We're looking at the spectral reflectance. And we're getting the reflectance is in the UV vis is roughly similar, right? So it's mostly infrared actually. But if you're looking at the black body emission, there's vast differences between doing this in 3D and doing this in 1D. And yeah, that's as I explained, right? That comes mostly from what temperature you assume for the black body. So yeah, so in summary, and then I'll go through some of the steps of how to work this, right? There's some scripts available on the GitHub webpage. The manual is available as well, and then we have the tutorial videos. And of course, you can always ask us. We're on Slack here. So now let me start by walking through how I did one of these simulations, and then I'll show you I can show the Python code. I don't know if that's common, Joe, like where we go and step by step on what sort of the strategy is, how I made this figure right here.
Maybe if we have time, or maybe we could take some questions before you show that part. But yeah,
sure.
Feel free to
okay.
do this first part. Yeah.
Yeah, that sounds good. And you're still seeing my screen, right?
Yes, seeing your screen with PSG, we can see the full window, including your desktop.
Okay, yeah, perfect. Yeah. So yeah, we're looking here. Let's start fresh. It's always good to start from a reset. Then you have the different templates here, right? A lot of these are our solar system. There's also a whole bunch of exoplanets. But in order to get to the globes application, you click on application, and we get here. There's a couple of templates in there. So we have the Earth here. Here are some of the settings that you might want to change. What we're going to do in this case is we're going to upload the 2 steps that we need to do. So I have here the GCM file, and I have here the configuration file that we're interested in. So I will first show you the configuration file, and I'll also show what happens when you essentially give PSG the wrong key for the binary file. Hold on, let me. Cool. Let's upload the binary file. This one. Yeah, so this is what you get when PSG misinterprets this binary file. So now we're looking here at the wind, or let's look at the albedo. You see that essentially the entire planet is misinterpreted. Honestly, you get really cool things out of this, because now we have some crazy kind of whatever you would call this. But the point is, you're not doing anything wrong. You're just giving PSG the wrong explanation for the file that you're uploading. So let me see if I can upload this configuration file that we're talking about, and then that should give a correct interpretation of the file. And there's something wrong with this configuration file, which is, I guess, a very appropriate way to demonstrate these things. So let's see what's happening with this configuration file real quick, and see if I can. I did modify this line. Otherwise, I have some other that should work with this exact same file here. No, okay, hold on. Let's go to the other folder. So we got our project here. And this feels deeply personal, because this is all my file structure, right? Like how do scientists organize their computers or not? And here we go. Now it works. So we upload our configuration file, and now it interprets the GCM correctly. So again, we're still looking at the winds here. And now what I would recommend once you start using globes is, once you have your GCM file and you have it uploaded into PSG, make sure that all of these make sense, right? So we have the surface temperature here. I'm going to disable these winds, and you see here we have the surface temperature. The range is 150 Kelvin to about 600. Red to blue, so that makes sense to me. The phase should be 60. That's the config 60 I uploaded. It doesn't quite translate here, but it looks good to me, so I'm going to take that. Surface pressure, actually, okay, so the surface pressure is higher at the back. I'll believe the GCM people with that. Then we have the atmospheric pressure at the 30 different layers that we have in this case. And you can just like sort of click through these and see if there's no like infinites here, or like sometimes the temperature all of a sudden is 10 to the 32, which is really just a problem with the interpretation of the file. And And then we have, in this case, there's some clouds in here, not at this particular height, but you can see if there's, I don't even know if there's ice clouds in this file, so doesn't look like it. Very often we use like 10 to the minus 30 as a filler file, as a filler number, because 0 is like, especially when you go into logarithm, like can give you some problems. Okay. Now the spatial binning, let's start with a spatial binning of what was demonstrated in a figure. Let's do 90. Let's hit simulate. And now we're getting this image back, right? So we're looking here at, this one has a pretty complicated stellar spectrum because we're looking at M body, reflected light here around 1 micron, and we get the emitted light here, the black body radiation maximizing around 7 here. So now let's see what happens once we start cranking up these calculations, and let's do the 10, spatial binning of 10, right? Now we get, there's what, 1, 2, 3, 4, it's like 12 simulations across the disk. And you see that the figure, the shape starts to change, right? Then what you can do in order to sort of verify what you're doing, if that makes sense, you can start clicking on these different points and look at what the orange line does here. So now we have the orange line, and we see that the orange line has its black body emission at around 12 micron, which corresponds to a very cold spot, right? So let's see what happens when we're more closer to the front. We see here, this is the figure, the image here. So we get reflected light here, and we get the much hotter black body here. And now if we want to crank this up even further, we can go to a spatial binning of 3. It's going to take a little bit longer, but this is still, it's a relatively simple planet, right? And then as we can see here, we can start, like, the shape starts to approximate what we wanted to see here, which is the difference between the full simulation, the 3D model, and the 1D model here. So the configuration file, it kind of speaks for itself, right? We have all these objects here. Again, like if you have any questions, you can always go to the it's under special keywords. So this is the list of keywords here that you can go through. The binary file, that's a little bit more involved, but essentially, as I mentioned, right, it's just a string of numbers. And important there is to really keep in mind that you have to supply PSD with the correct GCM parameter decryption key, essentially, to interpret the GCM file. So I see that there's a, yeah, okay, thanks for putting that in there. Let's see if there's any questions. Otherwise, I can go through some of the logic on how I do like a series of simulations. But I feel like I'm going to talk to my laptop for a while. So please, if there's anything that you're wondering, if that can you use this on your own GCM, or are you why are we doing things in a certain way? Please go ahead.
Yeah, awesome stuff, Vincent. I have a bunch of questions, but I'll definitely hold off till the end. So anyone's welcome to raise their hands or post questions in chat. I think I see one from Eleanor in here. Let's see. Aren't we supposed to get atmospheric features in the mid IR too?
That is a good question, and I think what it comes down to is the atmosphere is not very strong, right? So what we can do, Eleanor, is we can check this. Probably you could just and I think this is a cool test, because so here we're saying that the atmosphere consists of so was that 0.01 bars of CO2. Well, what happens if we upgrade this by a factor 10, right? Let's see if this this changes what we're looking at. So it's still not. That could be due to, I don't know if it actually read this in the correct way, because very often I would use a scalar in this case, because it's encoded within the see if this works. But yes, in principle, you should see molecular features here. And if that's not the case, then that's because I haven't specifically encoded that in the GCM or in the configuration file. And I don't know if at 0.1 bar, 0.01 bar, you would see CO2 in this case. Yeah.
Cool. I think Merrick has a question. Merrick, do you want to come off mute?
Yes, thank you. This is great stuff, Vincent. Thank you for the talk.
Thanks.
I have 2 questions. First one is the globes tool, if I pronounced that correctly, is it accessible through the API as well?
Yes. Yes, yes, it is.
Is that like you specify the one command that you added here with the GCM?
Right. So I'm still sharing my screen, right? So if I had this the Python code that I can share for that. So what you essentially have to do is there's 2 steps. So hold on. So the logic here is I make the configuration files in a set of folders first.
Yeah.
Then I generate the configuration files. Here's where I open them. But essentially, there's 2 lines of code that you need to send to PSG. And it is so I have a function here which calls the API. So you call the add globes, and with output type set, you can send the GCM file to globes. And then the next thing is you send the configuration file, and then you're asking for a different output type. And that's where you get we call it IMG, but it's a hyperspectral image essentially.
Yeah.
Okay.
Brilliant.
So yeah, okay. So those are both your questions?
The second one was on the amount of spatial binning, whether you have devices, what is the best? Is there a best?
That is a good question, and that is something that we don't quite have like a very positive answer for that yet, because essentially what we're seeing is that, especially for the Earth, right, because it's so complicated and so spatially variable, the more resolution we add, the more the spectra seem to change. And I would say for the simulation I've done for the Earth, there were about 6,500 calculations. And I think you could probably get away with doing that at a slightly higher binning, so maybe 2,000 or 1,500. But one of these full calculations takes about 30-40 minutes for the Earth, because the Earth is has clouds, it's got all the scattering, right? But as you could see, for these ones, these were pretty quick. Yeah, so yeah, that's a good point. And I think here that's definitely a question that is very GCM specific, and Mike Way is really pointing out there. And I think that's where those are the people that you want to talk to if you want to figure out what spatial binning you want to use. Just look at it's a combination of what your GCM tells you essentially, and what is feasible. And this is where the API is important too, right? Because if you can run these calculations on your local machine,
yeah,
you're not going to get kicked off the server. So that's an advantage.
Thank you.
Right.
Awesome. And there is a question in chat from Divya who asked, you mentioned about the Mira 2. Can you tell what exactly you're using that model for?
Yeah, so the Mira 2 database is used to track down the abundance of clouds and the abundance of I can break it down here. To use it for each of the data points in our GCM, essentially we have a varying amount of water, varying amount of O3, pressure and temperature, and then as well the liquid and ice cloud abundance. And I should say here that we've been puzzling quite a bit on how to include clouds in the correct way to simulate this, because the issue with clouds, if you have a very thick cloud deck, let's say you have a massive thundercloud right above Goddard, right? I can imagine that could happen for certain reasons. If you would calculate all of the cloud density as in spread out over the entire state of Maryland, that cloud wouldn't be very visible, right? Or it might still be visible because of the massive amounts of thundercloud that someone has summoned because they didn't get funded. But the way that we have to do this is actually we simulate a fully cloudy planet and a non-cloudy planet, and then combine those 2 images, which is why we have the non-cloudy situation here, which is sort of a byproduct of the method that we simulate these clouds. So that's why we use the Mira 2 database for. And if you have more questions, then I'm happy to answer them. Yeah. Okay. Cool.
Awesome. Anyone else have any other questions for Vincent at this point? Feel free to raise your hand, or you just come off mute or post them in chat. So I had one earlier when you were talking about the atmospheric structure in terms of the code. So you have these boxes. You showed a demonstration of it earlier. the size of those, like I assume you can change the size of them, but is there any like dynamic changes that are happening? So if the code detects that there's like a really complex layer in the atmosphere, will it try to shrink the size of those
Right.
steps, like adaptive
So
step sizing?
yeah, so the way that it works within PSG is that we have essentially, if we let me go back to the layering file, or the layering information. So in some cases, PSG actually does like something what we call sublayering. So if they're so for the Mera case, I think it's a little complicated because Mera doesn't define their cells as a function of height, but as a function of pressure. So the 72 vertical points that we use in this simulation, they don't actually line up with like a physical height and such, but we see that more often in atmospheric simulations, right, where we focus on pressure as the sort of the height value instead of the typical height that we're used to. But we've definitely, and this is an issue that we've been working on. I'm not sure whether we can see this in the simulations, but there are some issues that we do get when the layers and this particularly comes back to the cloudy simulations, where if the essentially the change is too rapid, so if the layers go from essentially from 0 to a relatively high value, we cannot calculate the derivative very accurately, or we can, but we get some problems. So I don't know if you can see. I might have like worked with these, but there's in some cases we get what we call fires. So I would be looking at simulations of like a crescent Earth, and looking at the intensity of the light getting back, and all of a sudden I would get like 1,000 times too bright pixels back, and that's like, okay, that is where the code essentially starts dripping up, and just like, yeah, struggling with sort of the layering scheme, because this specifically comes to this the multiple scattering code. So we use DieSort, which is used in the community very often. But the problem with DieSort is that it stops being very reliable below like angles or at high angles higher than 80 degrees. So that's where we'd had to go into like finding cases, and then sort of like providing some guardrails to make sure that the simulations didn't blow up, essentially.
Gotcha. Very cool. Yeah, I mean, while we're on this slide, like I just can't say how amazing this is, this simulation. Like I can't imagine how excited y'all were when you were first able to make this. I do wonder, is this, it's hard to tell with the clouds, but is this NASA suggesting that New Zealand is not real?
Is it still being recorded, Joe?
Is it still being recorded? Yeah, yeah, we'll talk about that offline.
We cannot go into the details on whether
okay, I understand.
that's real or not.
Sorry to bring that up.
No,
but actually, a real question: is there any sort of limitations on the rotation rate of the planet? Like, if you have a really fast spinning planet or a really slow spinning planet, does the code care about that? Is it happy with everything?
No. So this is where I'm really excited about, because I've been talking with a couple of people that have been simulating like different like rotation rates of Earth. You can have different eccentricities, and people just essentially like exploring sort of what this does with the planet, right? And so you can essentially, as long as you can get the GCM to behave and like sort of like come up with a coherent answer, PSG doesn't necessarily care very much.
Okay.
Yeah, and there's I mean, essentially the limitations are are not in the simulations. Yeah.
Gotcha. Very cool.
Yeah.
Awesome. Does anyone else have any questions for Vincent? Or Vincent, do you want to show anything else with the input file or the Python file you used to create this?
Yeah, if there's interest, and if we do have some time, I can just quickly go over sort of the logic of how we often do this. So what we found is the best way to do these kind of things is you want to keep the configuration file and the GCM files. Essentially, you want to keep this as well structured, right? So we open the configuration file, Then we modify the line which we want to change. So in this case, is the observer location or the observer longitude. And then I can change the GCM binning factor. Then I run the simulations on the local Docker. So we have this function called call API. So you send it to the to globes. You set it. So set means that you're sending a configuration file. But in this case specifically, the configuration file is this cruel, crazy binary file which you describe with your specific key, right? So you see here the first object of this this binary file is the code word binary, so that PSG knows that it's binary, and then it starts interpreting this exactly as you tell it to interpret it. So you send that, then you do another call with the configuration file. You get your file back. You save that into a different folder. Then if you get all these spectra, right, so you need to bin them correctly. So there's some function you can do that. Then you make images from all these hyperspectral files. So if you what you get back is this this file essentially with spectra at each location, right? So you need to weigh them appropriately, but then you can make this into an image as well by focusing on RG and B. So you have red, green, and blue at 450, 550, and 650. And that gives you like the color of the pixel, right? So that's how we get to these simulations. We get each pixel corresponds to a certain amount of light that we get, like reflected light that we get back. And then yeah, once you have those images and the spectra, you can just like put them together into a short little movie using this code. And I'm happy to share this. I can I don't know what your infrastructure for that is, Joe, but like the slides and the video and these configuration files, the GCM file, I can put it all up there.
Yeah, that's a good point. We'll figure something out for that, but that's awesome. Thanks for going through that. And also I feel like that I'm dumb, but I didn't really realize that, like, of course, like those colors that you're getting, those are like the actual spectral colors that you're getting from the planet. That's just incredible.
Yeah.
Awesome. Well, anyone else have any other questions or comments? I can attest that PSG is a well-used resource here at Goddard, and they have made it very easy to use. So definitely take a look at it if you haven't, to see if you can use it in your research. But
thanks, Joe. That means a lot. It's a lot of time and effort that goes into being accessible and trying to make it work.
For sure. Yeah.
Thanks.
Awesome. Well, let's thank Vincent for the great talk. And if anyone has any other questions for Vincent, I would be happy to put you in touch afterwards. But Vincent, awesome work and awesome talk going through everything.
Yep. Thanks for listening, everyone.
All right. Well, I will end the call here, but thanks everyone for coming out. And just as a reminder, our next exoVAST is going to be on March 6th, Wednesday, March 6th. But there's another VAST talk, just the virtual astronomy software talks without the exoplanets, on February 21st at 11 a.m. on the same Zoom, same channel. So thanks everyone. Have a good day. Take care.
Thanks, guys.